Alright, so we're going to look at number 11 again because we had some trouble because of one bad assumption I actually made. So if we look at the problem really quickly, they give us 3 particles, and they also give us the actual charge of each particles. We have 2 positive particles and 1 negative particle. And in terms of the wrong assumption we made is if we're trying to find the net force of this 45 microcoulombs, so we have to find the force that the negative 12 exerts and the force that the positive 18 exerts. So looking at the positive 18, we tried to make the assumption that we could use the x component of the distance to find the actual x component of the problem. But what happened there was that we actually can't use the distance to find the x or y components. For example, if we tried to assume that we were looking for the y component of the force, right? The y component of the force, if we assume that it's equal to k, q1, k2 divided by the y component of the distance squared, then if we were, that's not true. We actually get a really weird, crazy answer like we did in the class. The reason we get that is because if we look at the force of the y is the same thing as saying force sine theta, which equals k q1 q2 over r sine theta squared. So if we break down this equation to see if it's possible, we end up with something that actually isn't really likely and just kind of weird. Because then if we square the r sine theta, we get r squared sine theta squared. And then if we actually just try to get the f by itself and we get it out there, we get f is equal to k q1 q2 times r sine theta sine cubed, which is not the equation, right? The equation we want to get to is f equals k q1 q2 over r squared. That's the equation. So this whole sine cubed theta ends up kind of like giving us a false notion, which is why we kept getting the wrong answer. So the only way to possibly do this is to find the f, the force of that 18 microcoulombs exerts on the 45, and break that into its x and y components. So if we look at the problem again, and we put in our missing forces, what we end up looking for is we want to find the net force on that 45 coulombs. So we find the force that the negative 12 acts on it, and we got to find the force that the 18. Notice that the 18 is pointing down because the 18 is positive, the 45 is positive, so the 18 wants to push the 45 away, while the negative 12 wants to push the 45 towards it. So that's the direction of our forces. So if we start labeling F2 and F1, if we look for F1, we get F1 k q1 q2 divided by r squared, and we just plug in what we know using our distances. This one's nice and easy. If we can just plug it into our calculator, right? And we get that the force of 1 is 0.5394, and it's completely in the x direction. But it's actually in the negative x direction, which we need to incorporate later. So we can remember that. So then we look at the F2. The F2 is the same way. We start with the K, which is 8.99 times 10 to the 9. We start with the Q1, which is 40.5 times 10 to the 6, negative 6. And the 18 times 10 to the negative 6. But we run into a problem because we don't know what the distance between them is. But we can find the distance using trig. If they're 3 meters and 3 meters, and we're trying to find the hypotenuse, a squared plus b squared equals 18, and I take the square root of that to find the actual distance. Using that distance, we just kind of plug it in there, and since we're going to be squaring this, it kind of makes it nice and convenient. So then we actually go through the hassle of solving it, and we get that the force 2 should be equal to 0.405 newtons. Now, if we actually need to find the angle. The angle we can find using the inverse tangent of 3 over 3. If you needed to. A lot of you just see that the fact that it's a 3 side triangle, that it's actually 45 degrees. But if we did the inverse tangent of sine to find this angle here, we find that that angle is actually 45 degrees. Now the reason we found that angle is because we need to break this force 2 into its x and y components. So force 2x would simply be 0.405 cosine 45 degrees, which will give us 0.286 Now that's going to be positive 0.286. See, the force is pointing to the right. And the y would be the same thing except sine of 45, which would also give us 0.286, but that one's pointing down, right? Since the vector is pointing that way, the x component is positive, the y component is negative. So put a little negative sign there. Now that we have the x's and the y's, we can find the net force in the x by simply adding the x's. We have that negative 0.5394 plus 0.286, so the x component is going to be 0.252. We find the net force in the y by adding that negative 0.286, and that's the only one, so we don't have to really do anything else with it. And then to find the net force, we do the whole Pythagorean theorem, and that gives us 0.38. And then to find, a little backwards here, to find the tangent, the angle actually made, because we want to find the force and the angle, we would take tangent of the opposite, which is the y component, divided by the adjacent, which is the x, and then we get our angle, which ends up being 48.6 degrees or 49 degrees. And that's it.